All right, so I'm going to have fewer zombie slides, so you can check out if you don't like that. But yeah, I'm Dan Jurgens. I'll be going over our approach to adding Linux security support to InfiniBand. So the Linux security subsystem is a modular interface where the LSM provides a set of hooks to implement various security policy enforcement mechanisms, and then on the other end of the hooks, different security modules can register their own implementations. So our goal is to provide a set of hooks to enforce security on InfiniBand and provide the SELinux implementation to enforce a user-defined policy. So SELinux provides mandatory access control as opposed to discretionary access control like file permissions where the user can change them. SELinux doesn't allow users to make things available outside of the security context that they're in. You can use this to isolate users from each other or isolate applications from the rest of the system. And the mechanism used by SELinux is referred to as type enforcement. Every object in the system has or is labeled with a type, any object that you can enforce security on, and then you write rules that allow different types of security labels to interact. Oh, there we go. So this is a diagram showing how the IP networking stack implements security, or SELinux security specifically. There's a net filter and a net label module, and they can attach security context to outgoing packets and filter incoming packets based on the security context. So as you know, with RDMA we have kernel bypass, so this approach isn't possible for us. So a little diagram here showing that. So we have to isolate all of our security enforcement into the control path, creating and modifying QPs and things of that nature. So in order to do that, we've chosen to put a label on a partition. InfiniBand partitions are much like Ethernet VLANs. The subnet manager configures which nodes are in different partitions, and we can have a policy on the end nodes that allow certain users to access partitions to either limit their bandwidth or isolate them from other users. So let's go to the next slide here. Oh. So several new LSM hooks are needed to enforce security. Like I said, every object has to have a label. So we need to be able to associate security contexts with with something like a QP or a MAD agent. So there's alloc and free security hooks for the different object types. We need to control the SMI interface because we don't want to allow someone to launch a subnet manager and reconfigure the virtual fabrics. So in order to do that, we have a hook that you provide a device name, the port number of the device, and your level of security permissions, and that allows you to check if you have access to the SMI interface. For P keys, we've chosen to label them with the subnet prefix and a P key value to provide more flexibility. Instead of having a global P key namespace for security, you can now have the same P key used for different purposes on different subnets that way. Excuse me. So we need hooks to check whether a QP or a MAD agent has permission to use a particular P key. And then because the IB core module where the security is enforced is generally loaded as a module, we need a callback mechanism for SELinux or any other security module to notify IB core if there's a security policy change. Because we do all the security enforcement at QP modify and creation time, if you set up a QP and then the policy changed afterwards, you need to reinforce security whenever a change like that occurs. So again, to go over what we changed in the InfiniBand driver, we control access to the SMI. When registering a MAD agent, we check if it's an SMI MAD agent, if the user that's trying to create it has permission to access the SMI. Also, because of the possibility of a security policy change, we check all outgoing MADs on the SMI or we check all outgoing MADs, not only SMI, but we make sure that the MAD agent has permission to access the P key that the MAD is that the MAD is going out on, or the partition that the MAD is going out on, and if it's an SMI MAD, we make sure they have access to the SMI interface. So controlling QP access to partitions, we only allow users with permission to connect to QP on a particular partition. So when the QP is created, it inherits the security type of its creator. So if it's a user or an admin, the QP will be labeled with the same label as whoever created it. Whenever the QP is modified with changes to the port, the P key index, or the alternate path, we check that the new settings are allowed. If the QP is a shared QP, we have to make sure that every open handle of that QP has permission to change to the new settings. So the real QP will have its own security context, and then every open handle will have their security context as well. So we have to walk through all the open handles and make sure that every user of the QP can use the new settings, otherwise the modify will be disallowed. And then in order to enforce security when the P key or GID changes, similar to a security policy change, we need to keep a mapping of all the QPs that are using each port and P key index on each InfiniBand device. So if a policy or a port or a P key, or a policy or a P key table change or a GID change happens, we'll walk through all the lists for that particular device, make sure that the open QPs still have permission to use the new settings. If they don't, we will move that QP to error and raise a fatal event to the user. So some of the benefits of our implementation is that it's hardware independent. It sits in the IB core layer, so it's just work for any existing InfiniBand hardware. And then all the access controls in the control path. So while there might be some overhead in creating and setting up QPs, once everything's up and running, you'll still enjoy the full performance of the InfiniBand fabric. So this is an example of the new policy labeling syntax. So SELinux has a kernel portion and then a large user space set of utilities to write policy, compile policy, load policy, and things like that. So this shows the new policy syntax. And the main thing here is these P key cons and IB dev cons. Everything that gets labeled in SELinux has a con. There's a file con or an FS con. So the con means context. So you can see here we're labeling 3 different P keys. The default P key on the default subnet prefix with the default P key type. And then below we're going to allow both an admin and a staff user to use that, or I guess the allow statements are on the next page, sorry. And then we label two other ones, one with a staff allowed, and another that's admin allowed. So we can use this to isolate the staff and admin users from each other. And then we also label an InfiniBand device here for the SMI. MLX40 port 1. The admin is allowed to launch or to access the SMI on that device. So here's the allow syntax. Like I said, so the first line is allowing the sysadmin T type, which is for an admin user, to access the default P key and the admin allowed P key. The second 2 lines allow the staff user to access the default P key and the staff allowed P key. Excuse me. And then, I actually have a extra line on here, but the admin, this isn't actually in the demo, the second line that allows the staff to access the staff IB dev T device, that isn't actually in the policy that I'm going to show in the screenshots. So. All right, so normally I do this as a live demo, but I wasn't willing to gamble with that in this context. So the demo configuration we have is a staff user and an admin user. There's 4 partitions available. The default, which both are allowed to use, the staff allowed, the admin allowed, and then a neither allowed partition. And then, like I said, there's the admin allowed to access the SMI on MLX40 port 1. So I don't know how well you can see this, but at the top, at the top here I do the ID-Z and that tells you the type of the user that's currently logged in. So on the right side, you can see it's a sysadmin-t, and on the left side, it's also a sysadmin-t. So I run the command here on pkey index 2, which is the admin allowed pkey, and we can see that the test, the clients connect, the test is completed successfully, and the bandwidth is what you would normally expect for this type of test without SELinux involved. Here we have a staff user on the left and an admin user on the right. And we're trying to have them communicate over pkey index 1, which is the staff allowed pkey index. So you can see on the right side, the admin user got an init error with return code 13, which is an e-access error. SELinux always returns that error code whenever permission is denied. You'll see on the left side, they did not get an access error. They just had an error that involved not being able to properly set up the connection. There we go. Here we do the same test, except we do it on the, oop, I don't know what I just did. All right, so here we have the same test, except that they're using the default pkey now, and we see that the admin and staff user are able to connect and communicate over the QP that they both have access to. This is showing the limiting access to the SMI. Here we can see that it's an admin user. The port GUID ending in 22 is for port 2 of the card that's in use, and you see when we try to launch OpenSM, it fails. The error isn't especially helpful. I hear there's only 5 people that can update OpenSM, so we might have to talk to some of them to get a better error code or error message. But you can see in the second instance, the GUID ending in 21 is port 1, and the OpenSM launches successfully. So SELinux has a variety of tools to help administrators write policy and administer the system. Because we haven't extended anything about the way things are labeled, we've just made it so new objects can have labels. We can take advantage of all of these types of utilities that exist already. This is a utility called audit to allow. It walks the audit logs and looks for denials, and it shows you policy that you could write to effectively fix the problem that you had if you didn't intend to deny access to someone. So we can see here that this particular screenshot shows the different types of policy rules you'd add to make the fail cases that we'd shown actually connect successfully. We're targeting submission in the 4.7 kernel for the kernel changes. It's posted to the mailing list now as an RFC, assuming there's no major issues taken with the design. Hopefully we can get it incorporated quickly. The user space utility changes are larger and mostly complete, but we have to go through internal code reviews and submit before we can submit them to the mailing list. So until that's all done, it won't be functional. But hopefully the kernel changes are the most important to get in first, so we're focusing on those. With that, I'll take any questions you have.
How to do this. So have you done any performance testing on the additional overhead to send MADs?
No, I haven't done any testing for that.
When did you post the patches? I didn't see them.
I posted SELinux only on Monday, I believe it was, and then someone requested all of the IB core changes as well, so I posted those yesterday.
On Linux RDMA?
Linux RDMA,
Okay.
SELinux, and LSM mailing lists.
Okay.
I have one question. You mentioned earlier in the slide that this was hardware independent, but I saw a lot of things on the slide that said InfiniBand. Is it only independent for InfiniBand devices, or would it handle things like iWarp or other RDMA type of devices?
Well, since it's focused on InfiniBand partition control, it's primarily for InfiniBand.
Okay.
Thank you.